Hi everyone, I'm Erez. I'm from AppsFlyer, and I'm here to talk to you about modeling categorical variables using Bayesian networks. So essentially, imagine facing a data set having multiple categorical variables, okay? And we want to understand how all these variables relate to each other, how they connect to each other. So in this talk, I'm going to talk about Bayesian networks and how they help us model this situation well. So yeah, okay, cool, thanks. Okay, so first we're going to start with talking about the problem. The problem is that we have essentially a lot of application installs, and we want to detect fraudulent installs among all the installs that we get at AppsFlyer. And then next up, we're going to calculate the probabilities. We want to calculate the probability for an install to be fraudulent. So we're going to talk about that. What's the challenge in that? Why is that even difficult? And then what's the solution? How we deal with it? Hint, it's going to be using Bayesian networks. And then I'm going to talk about how we actually build this Bayesian network and how we use it to infer the probabilities. Cool. And eventually, I'm going to wrap it up and talk about some other models and why they don't handle this problem of multiple categorical variables very well. Popular models like neural networks and decision trees don't work very well. I'm going to talk about that. Okay, so first off, we're going to start with a problem. So as I said, at AppsFlyer, we get a lot of application installs, around 100 million app installs daily, and we have to detect fraud among them. Okay, and we have millions of frauds among these, so we have a significant portion. And essentially, our goal is to calculate which of these installs is fraud, and maybe we can calculate even the probability for an install to be fraud. Why is that difficult? So imagine we have about 20 different parameters of the install of the device, all these parameters about the device and the operating system and I don't know what. And then assume each one of these variables have, say, 100 possible values. Then all in all, we have the number of possible combinations we have for all these variables is like 100 to the 20 or 10 to the 40. So a lot of combinations is what I'm saying. So a lot of combinations, and in terms of runtime or memory complexity, it's just too much for us to learn all these combinations, and even if we had all this data available. Okay, so that's not really a valid solution just to learn each specific case individually. So there comes the naive Bayes approach. The naive Bayes approach says, okay, let's assume they're all independent. If all these 20 variables are independent, then we can learn each one separately, right? Learn its own distribution separately. So say we have maybe 100 possibilities for the first one and 100 for the next one, etc. So I have maybe 2,000 possibilities overall to learn. That's very easy. That's very nice to learn. It's not complicated. It's an easy computation to make. The only problem with it is that it's incorrect. Okay, we've assumed that they're all independent, which is not true. It's not the case in our data. Okay, if we take, for instance, one of our parameters is the device country and another one is the device language, right? Then you can assume that, okay, if the device country happens to be Russia, then the language of the device is very likely to be Russian. It's not nearly as likely to be Chinese, right? So clearly there's a very high dependence between these parameters, very high correlation. We can't assume they're independent. So we saw that if we assume they're all codependent, it just yields an intractable complexity. We can't really deal with it. If they're all dependent, if they're all independent, well, they're just not all independent. It just yields an incorrect result. So what we do with Bayesian networks is we actually try to model ones are codependent and which ones are not. Okay, so the Bayesian network is actually sort of a modeling of the relations between these different variables. We're actually going to have edges in this network between two variables if and only if they're codependent. That's what we're trying to do. So we want to build a network of these dependencies between the different variables to represent all these dependencies. And this way we hope to achieve something that is both computable in practice, okay, something we can actually compute in reasonable resources, and also something that will actually provide the accurate probability, or at least a good estimate as possible for the accurate probability for seeing a certain combination of these parameters. So on top of that, being computable and providing the accurate probability, we would also avoid overfitting in the way, since if we were to assume, like in the beginning, if you want to learn each combination individually, other than the other problems I've mentioned, this is actually pretty much the definition of overfitting, right? If we try to sort of fit a specific probability for each and every case, that's really going down to overfitting. We don't want to do that. And also, we even want our data to be explainable. We want, if we say something is fraud, we want to be able to say why it is fraud. Okay, this is actually a business requirement for us. So, so we're gonna win all these great features. The only question left is how do we do it? How do we build this Bayesian network? Okay, so we're gonna start off with a full network. Okay, so here in this example, I have 4 different variables: x1, x2, x3, x4, and we start off with a full network with all the edges between all the nodes. They're all connected, and in this case, to calculate the probability for seeing specific values of x1, x2, x3, and x4, we could use Bayes' theorem, apply it a few times, and we get probability for seeing x4 given x1, x2, x3 times probability for seeing x3 given x1, x2 times probability for seeing x2 given x1 times probability for seeing x1 itself. So this would be sort of our initial standing point, and this network is just essentially a graphical representation of this formula, in a sense. So we start off with a full network, but here we still have all the dependencies in place. We're essentially at the place of everything is codependent, and like I've mentioned in the beginning, this is too much of complexity to deal with. So we want to remove as many edges as we can. So say that x1 and x2 are independent, right? So if probability of x2 given x1 is approximately the same as probability of x2, right? They're independent. We're going to test this using chi-square test for statistical independence. So if they're independent, then we can move this edge from x1 to x2, and then I'm going to, okay, here, I remove this edge, and now instead of probability of x2 given x1, I just have probability of x2. I've also, if first I had to keep in memory all the possible combinations here of x2, all possible values of x2 times all possible values of x1 to provide all the values. So that would be 100 square values. Now I only have to keep in memory only 100 values for this node. Now something similar, say, happens with probability for x4 given x1, x2, x3 is the same as probability of x4 just given x2 and x3. In other words, given x2 and x3, x1 doesn't really add any information about x4, or given x2 and x3, x1 and x4 are independent, then I'm going to remove this edge from x1 to x4 and reducing the complexity here of this node a little bit, and then say, just for the example, that now probability of x4 given x1, x2 and x3, I don't even need x3, it's just enough to have x2, so I'm going to remove the edge from x3 as well. And now I'm left with a nice slim Bayesian network, which is, so here I went down from 100 to the 4 to 100 square here from 100 squared to 100. So I cut off my complexity significantly, and still able to reach an accurate calculation. So the final calculation given this network would be multiplying probability for x1 times probability for x2 times probability for x3 given x1, x2 times probability for x4 given x2. Okay, so this is the final calculation in this example of the probability for seeing all this combination of variables. What about explainability? If we take, for example, if we look at the numbers and we see, for example, that for x1 we get 0.6, for x2 0.5, for x3 0.3, and here for probability for x4 given x2 is, for the sake of the example, this number here, 0.0002. So a low probability. So I'm going to say, okay, this is really our fraud reason. Okay, the combination of x4 and x2 is really providing us with the fraud reason. Now you might think, Erez, come on, this is a stupid example. What are the odds for, this number is so much smaller than the other numbers? But I'm actually going to tell you that this is actually a fairly typical example of the data that we see. If you consider the example I've mentioned earlier, if you consider x2 to be something like the device's country, and x4 being something like the language, then if the country is Russia and then suddenly the language is Chinese, then yes, the probability of seeing Chinese given that the country is Russia is actually going to be very low, even probably a lot lower than this number. So, so yes, it is going to stand out. It is actually a fairly typical case for fraud that there's a certain combination of nodes, a certain node that gives us a very low probability. So it stands out in terms of explainability. We can say, okay, if this is the low number, then we can say this is actually the reason that the install that we see here is actually fraud, and that we call it out as fraud. Good. Cool. So we provided explainability. We built our model successfully. Now, I'm also going to argue that other popular models don't handle this problem very well. Why don't they? Essentially, this is a very uncontinuous problem, and other models are not built well to handle it. So in chaos theory, actually the definition of a chaotic function is a function where a small change in the input variables actually yields to a large shift in the output. This is exactly what we have here. What we have here is that I changed merely one parameter, say the language from Russian to Chinese, and suddenly the output shifts completely from being very unlikely to be fraud from becoming to being very likely to be fraud. So we have a huge output shift with just a minor input shift. And in general, we have a very, very uncontinuous, this is very uncontinuous behavior. So if we were to use models that are based on continuous techniques like neural networks, it's based on gradient descent. So essentially, it tries to find a local minimum, looking for it for something that is close to it in very continuous manner. It's not going to work very well, and it didn't work very well for this problem. When it comes to decision trees, they also don't work very well, since they also try to look for the most improving feature locally again, and they're not going to find all these combinations, and they're not going to work well either. So to conclude, we were able to compute the accurate probability correctly and accurately in a feasible time, provide explainability. It's a simple solution. It's not a black box. We can understand it. We can debug it. We can improve it. And in practice, at AppsFlyer, we were able to, we still use it in production. It provides actually an important portion of our fraud solution at AppsFlyer. So it's been quite successful for us. That's it. Thanks.